All right, rock on. All right, so I'm Owein. I'm from Media Math. We're an ad tech company. We have offices all over the place. I'm from New York, though, and we do a lot of cool stuff with Scala. We have, your standard big data, not like we're building something, and once we get enough customers, big data. We're talking like, we actually have petabytes of data. But my team, we handle a lot of, we have ad servers. So we're doing things with millions of requests a second and latency requirements on those requests in the order of milliseconds. And that's probably one of the reasons why I came to the company. The years I've been there, I've been enjoying things. I've been working with things in Scala. And one of the aspects, or one of the things that I've used in this code is recursion and some of these concepts. So when I come to these conferences, I often see a lot of really cool talks. I really enjoy going to some of the more advanced stuff because these guys are doing really amazing things, and I get to feel really stupid listening to it. But I often feel that there aren't enough talks there for a lot of the people that are rather new to Scala. Like, they've been doing a lot of languages, and they haven't really had concepts like this, like just here's recursion and here's what it is, and here's difference between recursion and tail recursion and why you might want to do this. So this is going to be one of those talks where I introduce a concept that's relatively easy to grok once you see it, but it's very powerful because it sort of is a gateway drug into some higher level abstractions, things that I won't get into, but we're going to look first at a small example. We're gonna set up a situation. We're gonna see some imperative code, how to look at that imperative code and what you would see there, and then we're gonna take that code and we're gonna compare it to a recursive version of that code, and then we're gonna contrast it again to a tail recursive version of that code, and we're gonna talk what we're doing with tail recursion and why it's different from all of these, how the compiler sees it, and how it can change and do what's called a tail call transformation. And then we're going to sort of move into another thing, which is a plugin I've been working on, which adds a feature that the language doesn't have, which is mutual tail recursion. So each one of these is going to build upon the other. But I'm putting this up because if you have computers and you want to open up and work with this, I'm actually going to do some live coding here. And if you want to follow along, I have it set up at this repo. All you need is SPT and a JVM, which if you're at a Scala, meetup, or I should say conference, you probably already have. And there's actually a couple other exercises in there if you want to do on your own. And if you want to speak to me afterwards or find me online or something, I'll actually help you. I don't mind taking some time out to go over this stuff if you have questions. So let's start. So we're going to set up a situation where we have just a tree structure, and we're going to make an assumption that this tree structure is non-empty, that there's always at least a node. So even if you have node and empty, that's what you're going to have. And we're also going to make the assumption that there are no loops. It's a straight up tree. So what we'd like to do is we'd like to walk this tree and figure out all of the leaves, which ones are the furthest, or not which ones are the furthest, but what is the furthest point from the root node. And if I do this imperatively, I get this function I'll just call longest. And if you're used to this style, it's relatively simple. You're setting up your search space. You're setting up the value that you've seen. And then you iterate through. As long as that search space has things to look at, you're going to pull out the highest, or the value at the current place, the node at the current, and then you're going to leave whatever's else there. And you're going to look at current. You're going to say, okay, if I'm empty, I have nothing more to look at. And if I have something on the left or the right or both, just sort of append it to the front of this search. So you are doing this is sort of a depth first traversal of the tree. And then I just compare what's my value now with the value that I've seen and take the greatest. And I could put this at the node, or at the, I should say, the leaf value if I really want to optimize, but max is, I mean, it's just like an if statement, you know. So that's it. I mean, this is the imperative version. You know, you probably grew up, you know, if you're steeped in doing exactly this in the languages that you've worked in. But I'd like to contrast that with the recursive version. And if you're counting, that's half the lines of code. We just went from 11 lines of code to 5. And they both produce the same results. And yet, if I look at this one, I know exactly what it's doing right away. I mean, this is doing nothing but exactly what the algorithm says it's doing. I'm finding the longest. As a matter of fact, you know, if you're looking at things in this state, or I should say in this manner, look at the boilerplate. I mean, in order to do this, I'm setting up two things. I'm setting up how to manage state, the value that I've seen most of, and what I've got to search through. And because I'm changing what I'm searching at each step, I have to sort of freeze where I am and capture that before I can move on. Whereas here, you know, I get my state management effectively for free. If I'm at the root node, node empty empty, and that's all it is, well, length is 0. I'm no distance from that node. And if there's something else to go, well, I'm just one more than the longest length of the child tree. And if there's both a left and a right, well, I'm just 1 plus the greatest, longest length between either my left side or my right side. And so if I'm looking for a bug, this being half the lines of code, I'm probably going to make half the mistakes. As a matter of fact, when I was setting this up, I wrote this one after I wrote the imperative one, and I looked at my unit tests, and I had a mistake in my imperative code. So, yeah. All right, so tail recursion. This has some sort of similarities to what we've seen in the imperative, but you can see it's actually quite different. I've set longest the way it is to keep the signature the same, but I'm actually doing an indirection to this method I'm just calling find. A lot of times you'll nest the function within your call and then recall it that way, but here it is again. I have a search space, and at each point I am looking to see, you know, what value am I at, and am I at a final or a leaf of this tree? And when I get to a leaf, I do the max comparison. I say, like, you know, is this value greater than I've seen before? Great, take that. That's the value that I want. And when I've run out of search space, I just return the value. So in many cases, what you're really doing, or what you're looking at and this sort of style or handling is you're setting up a structure, and your structure looks like this. A function with some arguments. I have a predicate on those arguments. Have I reached my end condition? Okay, if I have, return a value based upon those arguments. Otherwise, change the arguments a bit and call the function again. And if you really want to think about it at a true level, in terms of like how you would think about it with imperative code, is that I really have two sets of arguments. I have my arguments which are fixed and don't change between each call, and the state I'm trying to manage or handle. So one of the things that, you know, is difference between the recursive and a tail recursive method is the fact that there is, in many cases, an explicit handling of state, like you would with imperative code, but that state is managed at the argument level, so that you don't have to set up or do a lot of the boilerplate when you're looking at the direct logic. That state management moves to how you call the function. And you know, this has a nice structure that's so nice that Scala can actually, or Scala C can do something with it, and it can do this tail call transformation. You'll often hear people say like tail call optimization, but that's a misnomer. It's actually a transformation. What we have is we effectively have a looping structure here. So the JVM allows these things called labels. And if you ever read the JVM spec about these labels, they have like 3 paragraphs where they go, yeah, this looks like a go-to, but we have all these rules which make it not a go-to. But yeah, it's a go-to, straight up. So here we are. We've got again our predicate, the value, else change the state and go to our label. And we keep doing this until we're ready to exit. And that's it. You don't need to do too much more than that. But if you look at how this condition was set up or how we were managing this stuff, what you see is if you were to look at the call stack without doing this transformation, what you would see is function call, function call, function call, function call, function call, and the only thing changing is the arguments. Whereas if we look at this structure, what you're seeing is 1 plus the function call, and that plus is actually a function itself. That's a function call. So the call stack looks like longest plus, longest plus, longest plus, longest plus. So that's why you can't actually optimize this stuff, because the actual result depends not only upon the longest function evaluation, but then the evaluation of that result. And so, we have this TAILREC annotation. And notice that, I hadn't done that previously to the thing I called was in tail call position or tail called function. And that's because this TAILREC technically isn't required. If you want to do tail recursion, you can write it. And as long as it is, the compiler will happily optimize or transform it for you. But if somebody else comes along and they don't know, or they aren't familiar with the language, or they didn't realize what you were doing, they can screw it up. And it's going to happily compile, and then a couple weeks later, you're going to get a Stack Overflow, and things will go to heck. If you add this, though, the compiler is actually going to come in, and it's going to make a rigorous check, and it's going to say, okay, did you do this? Like, is this really a tail call function? Is every function call back to itself in tail call position? So what I'd like to do is I'd like to take us over and go right into some code here. I'll try and move this over here and minimize this, right? Minimize this. Does anybody know how to minimize something in a Mac? I actually really don't know how to minimize stuff in a Mac. Command M. All right, you know what I can do? I can open another window here. Sublime, file, open. This, open, great, and bring this over here, right? Wonderful, awesome. So now, since I can't actually see this, we're going to have exercise 1 here. So this, what I'm doing here is this is the one thing I don't like about Scala. Is like, Java did all these like nested folders. Like, why? Why would you do that? Other languages like Python, you just say like, here's my package name, done. So all right, I've got this imperative code here. This imperative code is, again, trying to deal with a tree structure. And All right, cool. That's way more readable. So what it's trying to do is it's actually going in and I'm giving it a tree structure, and this tree structure is going to be traversed, again, same way. But in this case, what I'm looking for is I'm looking for the largest weighted path. In other words, like if I... Bigger? All right. Bigger? Wow, that's awesome. Yeah, so I'm gonna look through all these things. This tree is gonna have an actual value. It's not gonna be an empty tree. And I'm gonna look through this tree and I'm gonna say like, all right, finding all the weights in this tree, I'm gonna add them all up, and then I wanna turn you the list of all those things that added up or sum up to the greatest value. So I've looked at tree, and it's really more than just a class here, and I added some sort of map because I could. We're actually not going to use that map. But if you think of it, it's just a bunch of leaves, which are a list, and a value at each node. And this is the imperative version. This looks great, wonderful if you're a big OO fan or work in OO land. And you've probably written something like this again. I'm setting up my search space. I'm setting up a list of values that I've seen. This is the actual result that's eventually going to be returned. And I'm just going to do this thing that sums up and holds things. So as long as I get to the leaf, I will actually take a look and evaluate these things. Can everyone understand what this is doing before I move on to the next slide? Because the next slide, I'm actually going to write it. Is anyone actually following along with this and doing it locally? No. All right. Well, good. That makes my job a little easier. All right, I'm going to do a git checkout. I'm going to change things slightly. All right, so here's this recursive version. So if you were following along right here, writing code with me, you'd be able to go home to like your wife or your husband or boyfriend or girlfriend or whatever. Be like, hey, hon, look at this. I wrote a recursive function. And they'd look back at you and go, wow, that's amazing. This is the most amazing thing ever. As a matter of fact, this is so amazing. You know that sports car you've been looking at? Why don't you go out and buy it? Like, it's totally cool. So once we get done with this, you're going to be able to go home, do that, show her, and be like, this is cool, or him. And they're going to love it. This is not recursive. This is not going to work. This is not going to pass muster. So how would I change this? What am I effectively trying to do with this? What I need to do, or what I need to recapture in this is that sort of state management for free. I need to be able to pass in a tree at each point, right? And then take a look at what I've got and handle it that way. So the first thing I should do is I should come up with a way of looking at sort of my search space. I should say, all right, awesome. All right, so I'm gonna redo this and use this as a guide. So what I really want is I want to make sure that my tree is doing something, right? Actually, wait, this is not the tail recursive version. I have to get that fancy. What I can do is I can say, okay, look, I've got a set of children, right? And tree's got leaves. So these are the things I'm going to search. I'm going to assume again that this is not an empty tree. It's got a set of leaves. And if I want to get the longest value out of this, well, I'm just going to do this, right? I don't have to get any fancier. Like, now I've got the longest set of things for my children. And so far, it's recursive. I mean, this is actually recursive, but it's not returning the result that I need. So now I can take this with this lovely set of values, and I can say, all right, tree.value, because that's the first element here. And I'm going to append this to the children longest. And now what I want to get out of this is the greatest value here. So if you were to look at the actual result type, this is a list of int. And to do this, to just get it out, I might do something like this. If left.sum is equal to right.sum, return left, or turn right, else left, right? This sort of works, right? This is going to return a list of strings. Does that make sense? So I've just taken this list of lists, and I've chosen the one that sums up to the greatest value. I've appended it to tree value, and I've returned that, and I'm done. This is all of, what, 3 lines of code versus I don't even know how many lines of code. So I can take this, erase this, call this longest, get really happy, and then walk over to tests. I have a bunch of tests here that I can run. And now, grabbing this and dragging it over here, and continuing to drag it over, and somehow not dragging it over, but still dragging it over. Oh, for the love of. All right, I'm going to run this here, and we'll see what happens. So I run test, and these will all pass. I know this because I've done this before. But what's actually going to happen is that when I come down to this crazy test here, that it's going to fail. So this crazy test looks at something, and it fails. And it fails because I'm actually not capturing a condition that I want to capture in this recursive method. And that's because if I have an empty list or something that has a negative value, list.sum is actually less, even if it's a longer set. So that's another words of saying that I could walk down the tree, and if the final leaf of that tree is like a negative value, I'm going to ignore it. So that's a mistake. And if I want to salvage it, I just do case nil, right? Right. And that's it. And this works. And this is the actual final result. And this is all of everything that you saw over here. So if you count this up, this file has 21 lines, and this has 12. Again, like half of everything that I wanted to do. And I don't know about you, but I find this much easier to read. And if I can drag this over here, you're going to see that all the tests actually pass. Oh. All right. And I have no idea how to get out of full screen. So I'm a Mac newbie, by the way. I've been using it for like 2 years. I like Linux. I've just never been able to figure out Mac yet. Sorry. All right, cool, awesome. So let me see. Oh, awesome, good. So that moves us on to mutual tail recursion. I'm not going to do the tail recursive version because we're going to run out of time. It is an exercise. I do have a couple branches if you do feel like doing it. There's another case later on, but mutual tail recursion. All right, so we talked about tail recursion and we saw what it was. And we showed how we can impress our friends and relatives and things like that. Now we're going to talk about mutual tail recursion. And Scala itself doesn't have this. This is something that I had to do as compiler plugin. I call it two tails. As a matter of fact, before I came to this conference, these slides looked different. And I went over to Adrian, and then I went over to a couple other people from Lightbend that actually work on SCALAC, and I actually got it working for a general case. And so I moved these slides, which I was just going to mention at the end and be like, oh, if you want to play around or anything, here you go, up front, because this, I think this is really great. I don't know about you, but I think recursively. Like, I actually don't like think in while loops or fors or anything more than, shall we say, a for comp over a monad or something like that. So mutual tail recursion. It's very similar to TAILREC. I mean, here we have ping, we have pong. Pong calls both itself and ping calls pong. And without this compiler plugin, if I were to write this the way it is, you get a Stack Overflow. If you chose something more than 65,000, it would just blow up. And there's nothing you can do about it. But with this compiler plugin, this works. It actually, behind the scenes, converts it all into a TAILREC function. And then I let SCALAC handle the real heavy lifting. But the question is, like, you know, well, okay, that's cool, but why? Why do you want to do that? And you know, the difference between the imperative code and the recursive code is one of conciseness. You know, I think if you open up your algorithms book like the CLRS or something like that, almost all of those things are defined recursively. And I hope that it's not the publisher looking at the professor and saying, like, no, more code means more ink. No, make it smaller. I'm hoping that it was actually something like, this is the way we look at it and think about it, because it is so concise. And being concise means that, in general, it's more readable, and more readable code is more maintainable code. So if you are writing tail recursive functions and you start needing to add in a lot of business logic, a lot of times what happens is each of those individual cases that you want to handle, like we had before, like a node with empty and a node with left, node with the right, or node with left right, each of those starts taking on more and more businessy logic. So if there is a mistake in it, and that code grows large, I have to sort of traverse down this stuff and find just that group of logic around everything else. But if I use with mutual recursion, I can take that code and I can stick each individual case in its own function, and therefore, you know, it's free of the clutter of the logic of business that it doesn't care about. So in this case, Pong only cares about itself, Ping only cares about itself, and if it needs Pong, Ping calls Pong, and that's it. So I'm using it is very similar to TAILREC. The one caveat being is, if you want things to be mutual recursive, they have to have the same type signatures. In other words, here's a function of arity 1 and a function of arity 2. These guys can't be TAILREC. And since they don't call themselves, and they have no even recursive structure outside of the way they've been set up here, this will fail compilation. But that doesn't mean you have to, in one class or one object or something, stick to a single, like, arity or single signature. They will automatically group. So 1 and 2, since they're mutually recursive, they'll form their own mutually recursive group. And foo and bar will form their own group as well. And the compiler will treat them separately, and will actually compile and just sort of work. And so if this does look cool and you're interested in this and you want to get it, the code's there, but this is up on Maven, and you can add it simply like that. Just include it into your library and, or I should say your code and go around and play with it. As a matter of fact, I really hope some people will go and play with this, because I'm sure there's more corner cases that I haven't uncovered. I've tried to be as explicit as possible, but you know, I've sort of run out of ideas of ways this could go wrong. So I need people to do things that I would never think of and then turn back to me and go, here's a bug. And if that works and everybody's happy with it, you know, there's potential that taking from a compiler plugin, maybe we could even bring it back into the language itself if I convince Adrian or one of those guys, like, hey, you know, this is something we actually want in Scala proper. And that would be awesome. So let me go with a working example. So I'm going to git stash. Or do I need to get stash? Do I have? Yeah, I need to get stash. Get stash, get checkout, master. Awesome. If I go over here, presentation, I can look here and I can actually see wow, I really can't see this. I should have thought about that. Main test. Test. Awesome. So I have this. I can take this. We can bring it over to command line here. Since I suck at awesome. Make this really, really big. Let me know if you can't see. And then awesome. Anyone got any questions so far? Anyone ready to fall asleep? Yeah, go for it.
Because it's a compiler plugin, it rewrites code. It organizes the code.
Because it's a compiler plugin.
It's a compiler plugin, it should do something with these functions. It should reorganize them in one function.
So,
can you repeat the question?
So yeah, so it's a compiler plugin. It should do something with these functions. It should rearrange them around or do something there. So what it's really doing under the hood is it's taking your code and your functions themselves, and it's taking the bodies of those functions, and it's sort of stapling together in a synthetic function that I recreate, and then I'm putting TAILREC in front of that. So that does have, I should say that it does have like two unfortunate sort of negative impacts, if you will. The first being that if you are writing something that is a large method, you can wind up not allowing the JIT compiler to do some really cool optimizations. If that method gets close to that 65,000 byte limit, it won't even try and do certain things. And I have to look at addressing that in the next version of the compiler plugin. The second thing is, yeah, I mean, much like pattern matching, it explodes. So you can actually get a really weird compiler error where it says like the method is too large. And again, you know, I have to handle that, but I've got a working thing, so that's, you know, baby steps. The next part is getting this stuff going. Import presentation. Am I in the wrong? Do I need to be in the project? Project. Okay, here we go. Awesome. So yeah, it is doing some magic. However, the visible to your functions themselves, they don't change. Like it sees nothing. You write them, you call them, you deal with them the same way it does. The transformation is actually in a new phase of the compiler that I put in before pattern matching and TAILREC. And so, you're oblivious to it. And that's part of the reasons I made it as a plugin compiler, because you can't sort of achieve the things that I wanted to do using macros, or not easily do it the way I wanted to, or I wanted to have it look in a macro context. Awesome. So I'm going to import presentation, and then I'm going to say value t equals new mutual recursion. And then I'm going to say, the heck did I call this? Mutual tail recursion. This is where I wish I had ammonite. Man. So I can make a really big thing, and it works. This is great. This is cool. But equals new without plugin wp dot ping 76. Yeah, that's pretty cool. Let's have more of that. All right, so I actually have a couple more slides, but I put them up in case we didn't even get this far. So I just wanted to talk briefly about this. So recursion is pretty cool. There are use cases for it. There are use cases where you want to avoid it. And sometimes working with these sort of constructs are what you want to avoid. But in this case, I look at this and I see, an imperative style thing. And I look down and I see something that's a lot easier to reason about, at least recursively. But there are cases where you just can't sort of do something like this cleanly in a recursive or imperative manner, as if like you're working with a flat map, or you're working with something along that nature, where you really do want to sort of try and make some logical switch based upon the value contained within your container object. So, we can look at some other things like tail recursively. But, just because you can write something tail recursively doesn't mean that it's better. This is a lot more code, and this is a lot less code, and it's actually, this to me is a lot easier to reason about and think about. So, things for the future, if somebody really does put in something like more than 65,000 times, or 2 to the whatever power, like, that's just stupid. No one's going to retry stuff that many times. Just, be sensible about it and choose like a recursion over a tail recursive manner. Don't try and be like super cool and really awesome and go home and like impress your friends and relatives and things like that. No parent's going to sit down with like another parent and look at them and say like, oh, my child wrote recursion. How about yours? No, that's not going to happen. So, I guess in closing remarks, what I want to say is be judicious with this stuff. I've got another example, another exercise in here that I knew we wouldn't have time to do. But it's up there. It's up there on this Git repo. And like I said, if you guys have questions, you want to play around with this. And for those looking at the video, if you also want to play around with this, here's my Twitter handle. I will help you out, but I'm also busy. So if I push it to Stack Overflow, it's because I'm busy. So do we have any more questions before we're done? Is that it? Awesome. Well, thank you very much.